All right, I'd like to thank the organizers for inviting me to speak. But okay, so today I'm going to talk about some stable transfer factors. So let me define what a stable transfer factor means in my case, and then I'm going to talk about some work that I've done on computing them. So let's let F be a non-Archimedean local field. We're going to say that the characteristic of F is not 2, is equal to 0, sorry. And the residual characteristic is not equal to 2. All right, so as has been discussed numerous times thus far, so this idea of Langland's functoriality says that if we have two reductive groups, H and G, defined over F, and we have some homomorphism between their L groups, this ought to give rise to a map between L packets of representations of H to L packets of representations of G. But moreover, as has also been discussed, you can assign to an L packet a stable character, which is just some nice linear combination of the characters of the various representations in the L packet. So equivalently to this, you can think to this homomorphism, we can assign a map between these stable characters of H to the stable characters of G. So basically equivalent ideas, but an idea of that's explicated in Langland's paper Singularité et transfert from 2013 says that perhaps we should take this second view of functoriality and try to make it more explicit in the following sense, that we should seek a distribution. So let's call it K on the product of G times H. And I'm lying somewhat. We don't necessarily want a distribution on this product. We more generally want a distribution on the product of the Steinberg-Hitchin bases, but for today we can often generally just work on the group, so I'll write all my notation as if we're working on the group, such that this distribution realizes this equivalence expressly in the following sense. Suppose that you have some stable character of H that's mapped via this correspondence to a stable character of G. What we want is to be able to compute this stable character of G via, so this isn't really an integral, it's a pairing of distributions, but I'm writing it as an integral, as is often done, as follows. So we want a distribution which explicitly realizes this map here. Okay? Pardon? Over H, yes. Yep. Right. I was omitting H because perhaps I should actually write the Steinberg-Hitchin base, but yes, I'll write H. Yep. So a distribution over H. So, and we're going to call this distribution the stable transfer factor. And why we call it this is this talk's going to focus on computing such a factor, but what one would like to do with such a thing is to utilize it for stable transfer of smooth functions from one group to another. So this is how it works on characters. So the idea is dually, what we'd like is for it to have some operation on stable orbital integrals in the following sense. If you have some smooth function f superscript g, smooth compactly supported on G, we'd like there to be some transfer function on H such that the stable orbital integrals of H of this function H, f superscript H match those on G in this following sense. So times this distribution. This time doing this on G. And I'm omitting some fairly important terms here, some normalization terms which appear when dealing with the Steinberg-Hitchin base, but I'm going to drop them for now. But so what we would like for this stable transfer factor is to also have this stable transfer of functions. This latter bit hasn't been worked out in many cases, but it's what we'd like. But today I'm going to talk about the computation of the distribution itself. Okay, so, and of course this is sort of an analog in this stable case to what happens in the case of endoscopy with the endoscopic transfer of functions. So a natural question is, in which cases is K or the transfer understood? And the answer is very few at this point. For one thing, I know that there's work of Shellstad being done in the Archimedean case, which is work in progress, but I'm focusing instead on the p-adic case here. So an example where everything is known is the case where G is equal to SL2, and the group H is just a torus, which is maximal and elliptic. And this is in fact the work of Gelfand and Gryaev way back in the 1960s, and also discussed again in Langland's recent paper. So what does this say? So Lay talked a little bit about the representation theory of SL2 in a previous talk, but I'll just recall some of the things that he mentioned. So in Gelfand-Gryaev's book, Generalized Functions Volume 6, you can see that what they're able to do is to some character of this maximal torus. They can assign a pair of representations. Let's call them pi psi plus and pi psi minus. And these are going to be supercuspidal representations of SL2. And just seeing how they go, they want to consider the character theory of these two guys, but they find that somewhat difficult, and they find it easier to work with. And let's refer to their characters as chi psi plus and chi psi minus. But indeed, in computing these, that's a little tricky, so they find it easier to work with the character of the direct sum, chi psi, which is the sum of these two characters. That is to say, the character of the direct sum. But this character has the advantage that it is stable. That is to say that it's stable under GL2 conjugation, not just SL2 conjugation. And they make this parenthetical remark that, and truth be told, they didn't fully prove this formula as written. They may have had full proofs, but they certainly didn't appear in their book. But they make this parenthetical remark that it's easier to consider the Mellin transform of these characters to write down the character formula. So what they compute, so theorem of Gelfand and Gryaev, is that if you take the integral over the characters of the torus of chi psi of G times this guy here, so just the inverse Fourier transform, in fact, what you get is the following function. Just 2 times a character applied to the trace of G minus the trace of T, all over just the p-adic absolute value of the trace of G minus the trace of T. In fact, the same formula is going to hold for Archimedean fields as well in this case, where sine of T is the quadratic character associated to the field E times, which is what the F points of T look like. Yeah. Okay, so, but note that this is exactly what we want in this particular case. So in the case of SL2, this guy here is our stable transfer factor. Why? Well, luckily I still have this integral written up. Well, what we have here is we have, in this case, that we want to say the character of the representation on G looks like the integral over T of this distribution times the character. But we're in this nice abelian case, and we can use standard harmonic analysis. We need to use some distributional methods, but nonetheless, how do you isolate this term? Well, you can just do that by taking the inverse Fourier transform of this side to rip out this term here. Okay? So that's what worked in their case. So this was way back, and they weren't considering anything to do with stable transfer or anything when they computed this. Yep. Yeah. The character group of the torus. Yeah. Yes. I apologize. Yes. D side. Yes. You have to go over the character group of the torus. Okay. So, it's this function of T. I'm not sure if I understand the question. Okay. Okay. So furthermore, another case, which I worked on in my thesis, is the case of G is equal to SLL, L an odd prime. This seems like somewhat of a strange condition to say SLL as opposed to SLN, but the character formulas for the supercuspidor representations are much nicer in this case. And the group H is again just a torus inside of G. Let's say T is maximal elliptic, and let's go even nicer and even assume that it's unramified. All right, so to compute the stable transfer factor in this case, I want to use an argument similar to that of Gelfand and Gryaev, but I need a bunch of pieces in order to do this. So all right, so how to compute KGT in this case? Well, what did we have in the case of Gelfand and Gryaev? What we would like is to be able to explicitly write down a mapping for any time you have a character of the torus to give out a stable character of a supercuspidor representation of SLL. All the representations that show up in this case are going to be supercuspidal. We need a character formula for the stable character chi psi. And then what we want to do is we want to compute the stable transfer factor as this Fourier inversion. Okay, so So that's what we'd like to do in this case. So there are some simplifications since we're working in the case of SLL, and which are fairly nice. So fact. So in this case, stable characters of SLL are restrictions of characters of GLL to SLL. So basically what we need to do this is all we need is to know a construction of these various supercuspidal characters for GLL, and we don't have to worry about stable anything. We can just work on GL, and then we have to work through a character formula and then ultimately perform this integral. All right? Yes? Yes. 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 Mm-hmm. So what's the meaning of this side here? Well, this character was the sum of the traces, right? So just this character here is the sum of the traces, and then we take all of the traces together and we sort of amalgamate them and we perform this integral thereof, right? And then, I mean, I wasn't going to talk about the sort of stable transfer side of it today, but indeed, essentially by what I said before about the Fourier inversion back and forth, is you can check that, and for example, Langlands does this in singularité transfer, that indeed this is the formula you want here. Yeah. But indeed, yeah. So this is you can think of sort of G as fixed for the most part, and this is our distribution on the torus represented by a smooth function. Is that fair enough? Okay. So, all right, let me, so similarly, I suppose, in the case of SLL, we have the similar case, so theorem. So what this formula looks like in the case of SLL is the following. So for G stably conjugate to an element in the torus, we have, well, this guy is no longer a smooth function, but is genuinely a distribution. It's equal to the following formula. There's some constant, and then you multiply that by power of q times the minimum of the p-adic depths of the elements G and T. Sorry, I'm running out of room here. But then plus, you also need a couple of delta mass distributions. So so yeah, so for this formula here, it's given by this quantity here. That's for G in the stable class of the torus, whereas for G not in this stable class, we get a similar formula, but summing over various conjugacy classes in the Lie algebra. It's given by So I'm leaving the definition of these constants somewhat mysterious, but they're quite easy to write down. I just don't want to write them out just due to board space. But, okay. So, yeah. Pardon? I was just about to say that. So, all right. So let me, I had to erase it due to room, but, so the formula of Gelfand-Grajov is a lot prettier because of how concisely you can write it, but remember, in their case, they have the formula of the sine of the trace of G minus the trace of T all over this p-adic absolute value. But let's look at this. If you actually compute this out, the denominator, what's happening, if you take the difference of these traces and take their p-adic absolute value, what you're basically going to get, if these elements aren't too close together, is q squared times the minimum of the two norms. So that's how this is going to relate, because if L is equal to 2 here in this torus case, you get 4 plus 2 minus 2 over 2, which is 2. All right, so that's how these two formulas relate. In the L is equal to 2 case, because the character formula has sort of a -1 to the n in it, you're going to get this sine term up top, which isn't going to appear for odd L. And moreover, of course, in this formula, as G and T get very close to one another, you get this singularity in the denominator, which we don't see in this part of the formula, but it's roughly, instead has this sort of distributional point mass incarnation instead. Not something as clean as theirs, but it certainly agrees. It's non-obvious that this second term, but this second term works out the same way. There's, of course, only 2 classes of nilpotent orbits in the Lie algebra, and it also can be shown when you plug a split element into here that you also get the same formula. But no, I don't have anything as clean as this. So, any further questions about the statement of the theorem? All right, so going forward, let me just talk a little bit about these various steps that I wrote out, sort of how to go from a character to a stable character, and how to talk about the character formula for these guys. So to do this, I need a construction, a fairly recent construction of supracuspidal characters due to Howe and later on of U, and then a formula for their values given by De Backer, Adler, and Spice. So let me just mention this. So, so construction of supracuspidal characters of GLN. I'll write out the case of GLN, but we'll restrict to L going forward. But, okay, so what do we have in this case? So in Gelfand and Grajov and Petesky-Shapiro's book, they have very, very explicit operators that they can just write down. The operator is equal to this, and they have these nice integral representations for their various representations. We don't have anything as nice in this case, but we still have a construction which we can use. So the construction of Howe, I believe in the 1960s, 70s. So I'm going to talk first about Howe's construction and then relate it to U's construction, because we need to use the U's construction method to use the character formula. But what Howe showed is that exactly as we have anytime you have some character of the torus, of a maximal elliptic torus of GLN, let's say that it's admissible, well, you can take psi and you can assign to it some representation, pi sub psi, so supercuspidal rep of GLN F. But moreover, sort of what happens here is more specifically, what Howe shows is it's sort of an inductive construction. It is, as you would want, ultimately a compact induction from a compact open subgroup of GLNF. And what Howe shows is that psi has a Howe factorization. So you can write psi is equal to a product of characters psi sub 0, psi sub 1, down to psi sub d, where we have that psi sub 0 is just a genuine character of E which doesn't factor through a norm map, but going down, we have that psi sub I factors through some norm map, other way around, factors through some norm map of a smaller field, where we have that, we have a tower of fields. E is equal to E0 containing E1, containing ED, which is equal to F. And this is unique if we assert that the depths of these characters increases as you go down, where the depth of characters is basically basically the conductor of the character. Okay. And then he uses this factorization to compute supercuspidal characters of GLN. But what we need is not only a construction of these supercuspidal characters, we'd like a computation, supercuspidal representations rather, we'd like a computation of their characters. So for this, what we need is recent character formulas. So this is fairly recent work by Adler, De Backer, and Spice. And I'll just talk about this verbally for a second. What they were able to do is to any supercuspidal character, supercuspidal representation defined via the construction of U, which I haven't mentioned yet, they're able to spit out a character formula for such a representation, and we use that representation in our computations here. So let me briefly mention something else about this Howe factorization, and then I'll mention U's construction and talk about the character formula. But first of all, here, note that from this Howe factorization we can build the following. Let's let Ti inside of T be a subtorus with the F points of Ti look like the unit elements of this field EI here. And then let's let GI be equal to the centralizer in G of the torus Ti. And then what's that going to give us? That's going to give us a tower of groups which are in fact not Levy subgroups, but twisted Levy subgroups of GLN as follows. So going down GD minus 1, all the way down to G0, which is just T itself. So from Howe's factorization, we can sort of take this factorization of characters and build up this tower of subgroups. And it was an observation that I first learned in a paper of Tosho that relate it use construction to just a Howe factorization, but use construction looks just like this, but in further generality. So JKU gave a construction of supercuspidal representations for reductive groups over F, and it has a bunch of nasty looking pieces. For example, like the datum that he has to take in to build a representation is a tower of twisted Levy subgroups, a collection of characters, each of these Levy subgroups as follows, and also some other data. He needs some point in the Bruja-Titz building, as well as a specific type of representation of the group G0. But in our case, we can simplify this tremendously because in our case, this just reduces to Howe's construction. All we need from this is that this tower of groups is just as follows, and this tower of characters is exactly the ones that we wrote down there. So why I'm writing down all of this, and I know that this is a little notation heavy, is that in the language of Adler, de Backer, Spice, they wrote their character formulas for representations made in this case, but suffice it to say that Howe's construction agrees with U's construction for GLN. And we have the following character formula. Again, by a series of papers by Adler, de Backer, and Spice, which allows us to compute the characters of these representations. So what we have is that the character of such a representation may be computed as follows. So what we have is it is given by, just write this down properly. So you take this last character and just apply it to the element G, but then you need the discriminant of the element G, and then you need a nasty looking sum for G in a certain set, which I'll omit, just such that it conjugates these elements nicely into this group one tier down. So you start with an element of G, and you sum over a, it's a sum over elements such that if you conjugate part of this element G, you get down not into the full group, but in one group down. And then there's two terms which appear in this formula. There's a first term which basically deals just with some stuff dealing with the terms, again in a paper of Tosho, this first term is just related to the root datum of the group and actually looks a lot like some terms which appear in the endoscopic transfer factor for these groups. And then you multiply this by the normalized character of one representation down. U's construction is inductive, so you have to first build a character of G0, then G1, then G2, all the way up. And you plug this guy in here. And then there's also an orbital integral, which a Fourier transform of an orbital integral, which appears in the formula. Okay, So this looks like a bit of a mess, but it's nice to have a character formula at all. This was unknown until I think around 2012, these papers started to come out. And remember that prior to this, we only really had character formulas for supracuspidal characters at all in the case of GL2, but now we have a nicer formula that works, well, at least a formula that works for most supracuspidal characters, except we do need a slight restriction, assuming that G d minus 1 is anisotropic mod the center. So this is a fairly critical assertion. Basically, for GLN in general, if you have this long Howe factorization, you're never going to have this happening unless you just have the d is equal to 1, and you essentially have a single term in this Howe factorization. But that's where this assertion that n is equal to L is prime comes into the case. Basically, this character formula is not exhaustive for all characters unless you're in the case n is equal to L prime, in which case you do necessarily get this nice compactness result to which you can apply the character formula, right? Because let me just explicate that down a little bit. If we have n is equal to L prime, we can only have that your Howe factorization has two terms, psi 0 times psi 1, where we have that just the group GD is just equal to GLL itself at G1, and G0 is just the torus, which, since it's elliptic, it's indeed compact mod center, which is what we need. Okay? So this is where that strange assertion that L must be prime comes in. It comes into this character formula case. More recently, Spice has written a recent work which removes this condition, but as of yet, in the case of my thesis, I just used this, I just considered the n is equal to L case. Okay, but, sorry, is there a question? Pardon? No, it can be, n can be equal to 2 also for this to work. Yeah. Yeah, no, everything about this method should work in the composite case so long as we have a character formula like this, which we now do, but we just didn't at the time. So I'm restricting to this case for now. But in fact, what we can see is that this somewhat yucky formula does have a simplification in the case of GLL. So fact, we may simplify this formula. So in fact, it works out quite a bit nicer than it appears. So for G in the torus, at least, so for G, let's just say in the torus, but what I really mean is any element that's conjugate to an element of the torus, we can in fact simplify both this first term as well as this latter orbital integral term and actually get a nice formula, which is a lot easier to work with. We have the character formula here is just given by so just Q to the minimum of the depths of G and psi to the power of L squared minus L over 2 times just the sum over the Galois group of E over F, where E is the extension corresponding to T, of you just take the character of G and take its Galois conjugate. All right. So when all is said and done, basically this first term is contributing this sum over the characters, and this latter bit, this orbital integral bit, in this fairly simplified case, just works out to this power of q. Okay. So, and then indeed, I go further in my thesis. Once I have this formula in hand, I'm able to compute that Fourier integral, which gives the factor in that case. Okay. All right, so it seems this took a bit more time than I intended, but let me just say a little bit right here at the end about some recent work that I'm doing. So further cases. So in this current, so in the case, this is joint work with Gill and Woe. We're considering instead now the case of H is equal to GL2, G is equal to GL n, but let's say 3 for now, and where this map between the L groups is just the symmetric square power map between these L groups. All right, so, and what happens in this case is, well, there's an issue which arises. And that's the fact that H of F is non-abelian. So in the cases I mentioned previously, the group H was always just a torus, and how could we compute what we wanted to? Well, in this definition of what we want to be the stable transfer factor, you don't really have to worry tremendously about the Steinberg-Hitchin base or anything like that. You can just consider a nice integral over an abelian group, and then to get the stable transfer factor distribution, you can just use Fourier inversion. But in this case, of course, our life is a lot more difficult because our group is non-abelian. But we can remedy this fact slightly by looking at, so what I'm going to discuss is not the entire computation of the kernel here, but sort of a bit of the kernel that's nicer and easier to compute. So let me mention what goes on here. So, recall for the representations, let's say admissible representations of H, well, they come in a number of flavors. We, of course, have the principal series. We have the Steinberg representation and its twists. And these, I'm not going to talk about too much what happens there, but if, sorry, what did I say? God. I apologize. No. I appreciate input. Yes, so principal series, not principal. Yeah. But so of course I'm not going to mention them, but of course we also have the supercuspidal representations, which, as I mentioned before, are parametrized by pairs T, E, and some character psi, a character of the torus TE, where TE, the f points of this torus are just E times for E some quadratic extension. So I'm going to talk about how we deal with these terms here. So of course, if we have F is a p-adic field, characteristic 0, and we have that the residual characteristic is not equal to 2, in fact, we only have 3 quadratic extensions here, just the unramified and the 2 non-isomorphic ramified extensions. So the supercuspidal representations essentially, fully just fall into these 3 families. So what I want to talk about here is what the symmetric square power does to these representations, and then how we can compute this stable transfer factor kernel, given that information. So how am I doing for time? Okay, cool. All right. So in fact, looking at the associated Langlands parameters, well, what we have is if you have this sim squared map, well, what does it do to this representation, pi sub psi, for psi in this pair? Well, in fact, we can show exactly where it goes. It goes to a representation, I guess let's call it capital pi psi. So this is a representation of GL3, but we can even write down explicitly what it is. It's the following. It is obtained by parabolic induction from a representation of the Levy subgroup GL1 times GL2 inside of GL3. And we can even write down what representation it is, and that representation, something I'll call eta, I guess, eta psi, which is a rep of M, is just the character psi tensor with the representation of GL2, which corresponds not to psi itself, but psi squared. Okay? So then what we can do with this is now we can apply a character formula to this, explicitly get the character of this representation, and then do something similar to in my previous work where we do something like a Fourier transform. So note, so this representation we get, capital pi sub psi, so it is not a supercuspidal representation, it's an admissible representation, but that is actually fine. So fact, so this is by work of Van Dijk, I believe in the 70s, in 1972. So the character of capital pi sub psi may be computed via Well, so its character is just, so take the sum over this Weyl set, that is to say the bijections between the split component of this Levy subgroup M to the split component of G, which are just restrictions to Weyl elements, and then just the discriminant of this conjugation of G for M divided by the discriminant of the same element for G, both to the 1/2, and then times this character of the Levy subgroup. So let me just emphasize this point. So this work of Van Dyck happened way back when in 1972, so way before any supercuspidal character theory was well understood except for the case of GL2. But basically what Van Dyck computed is that if you know how to compute characters of supercuspidal representations, you can in fact compute characters of admissible representations if you know the supercuspidals of levies that they were induced from. So now that we actually have character formulas for supercuspidal representations, we can go back and use this work of Van Dyck to talk about what to explicitly, explicitly compute the characters of these representations of admissible representations. Okay, so in my sort of remaining minutes, let me say something about how this computation goes in this particular case. So, and note moreover that what is this guy here? Well, this I can simplify further, because how does it work? Well, let's say that you have some element, so this element G, let's say it's given by some lambda in GL1 and some mu here in GL2. Well, you can compute this character, I guess I called it eta psi before, exactly as follows. It's just, you take the character psi and you apply it to, I guess you could just call this lambda, or you could call this the diagonal matrix with lambdas along the diagonal, and then just times the character of this representation here applied to mu. So this is quite well understood, quite easily understandable rather. So we have this nasty representation of GL3, which isn't supercuspidal, but we can understand its character perfectly well, and it basically just reduces to our character theory of GL2, which we understand completely. All right, so finally, for what shows up in the calculation of this factor is, and I'm absolutely omitting some details here, but I'm sort of going to give the flavor of part of the computation. So to compute this guy here, well, what we want to do is roughly the following. So we want to do some sort of Fourier inversion. So part of this is sort of beyond the scope of this talk right now. It gets a little complicated for, say, when you're dealing with things in the principal series or others. But for the supercuspidal pieces, you can recall that we have some nice results about what's it called? Independence of characters for discrete series representations. So we can compute part of this kernel essentially as the following. Let's say you just want to integrate over the supercuspidal part of the spectrum of H, and just sort of a very similar integral as in the case of my thesis for tori, where you take the representation, the character of big pi psi at G times little pi psi. I shouldn't call them this yet. Let's just call them pi and I guess sim2 of pi d pi. But in this case, everything is supercuspidal, so we don't have to worry about anything nasty about the Plancherel measure. These are all just point masses because everything is supercuspidal. But what this works out to, therefore, let me just write this down properly, is you can basically just say that what is this? Well, it's just, first of all, what we can pull out is just the sum over these guys in the Weyl set. Let's not worry much about this term. It's not really the point, but I'll write it down for completeness. But then we know that these supercuspidal representations are parametrized by quadratic extensions. So what we really get here is a sum over E over F quadratic. And then more specifically, we get, as I worked out before, so the character of the representation corresponding to psi squared of, and again, let's call G. Pardon? So the lifting, the map between L groups is sim squared. So I'm just saying, start with this representation pi, and where does it go under this map between L groups? That's, yes. Indeed, since I'm just calling it pi and not pi sub psi, I needed some notation for it. So the representation of G, which corresponds under functoriality to the representation of H. Fair enough? I'm just, yes. Indeed, so sure, but after this line, we can actually compute what you're going to get. Yep. So indeed, because everything's supercuspidal, we do know exactly what we're going to get, hence, retroactively justifying the notation, is that you get this representation applied to G times this representation according to psi applied to H inverse. You also need this psi of lambda comes out. And then let's call it, and this is, of course, an integral over the dual of the torus TE, dE psi. So we can relate what was this Plancherel integral to just an integral over 3 distinct tori, where you take something that just looks like this, this product of these 2 characters with this other term that also appears. All right, but with some formal manipulations, which require justification, justification's there, I just won't talk about it at the moment. Basically, what you can work this out to is, so let me just look at this term here for a particular torus. Well, what is this term equal to? Well, I can replace this character with an integral over the torus of the kernel for GL2. So I can take this character, and what I can do is I can say that what this really is, well, let's take an integral over 2 copies of the torus itself, and I can replace this guy with the relevant kernel for GL2 of G times T1 times psi squared of T1 not inverse. And then I can also do the same thing. I can replace this character here with the kernel here, and also introduce this guy. Oh, and of course T1 needs to be squared because we're using the character squared, and then we also have this guy lambda here coming along for the ride. So what I'm suggesting here is, since we can replace this character with an integral over the kernel, and similarly with this one, in principle what we can try to do is try to build new stable transfer factor kernels from old in this sense. And then going further, I guess I'm out of time, what we actually get here, when all is said and done, is we can reduce this integral, sort of noting that these kernels can be realized as limits of smooth functions. What you pardon? Yes. No. Right. No. Psi was squared, so we applied psi squared to T1, which is just psi of T1 squared. Yeah. So this works out to a quantity which needs to be regularized to make sense, but basically what you can do is you can compute the convolution, let's call these KE, the convolution of these two kernels. Pardon? Yes, yes, I'll be done as soon as I write this line. Yep. The convolution of these two kernels, let me just write the correct term in here. Yeah, sorry. Which, because I'm plugging in a value into a distribution, I need to put sort of quotes here, but there is a regularized value that makes sense. So the upshot is, basically, to compute a large piece of this stable transfer factor kernel, we can build up new kernels from old and compute something like this in order to get our stable transfer. Okay, I'm out of time, so thank you. Yes. So that, in this particular case, I would need to go into some details that I haven't mentioned here, but I just, indeed, remember that this isn't the full kernel. This is just sort of a piece of it. I just wanted to, within the bounds of a 1-hour talk, explicate that sort of an important part of this kernel can be built up from old kernels. But no, absolutely, this isn't the full picture. We need to consider the other pieces dealing with the other parts of the spectrum. So this isn't a full answer. Yes, yeah. I believe so. With some slight, there are some extra terms that show up. This is Yeah, orthogonality of discrete series characters. So there's another term which applies, but yeah, that's where this part of the computation is coming from. Yeah, no, of course, this is too naive to do over the entire, and absolutely I agree, but because everything here is a discrete spectrum, we can cheat a little bit to get this part of the kernel in sort of a nicer way than you'd expect. In principle. Yes. Yes. Not yet, but I mean that's absolutely something that I'm trying to seek out by working with these examples. That's absolutely a goal, but no, I do not know any examples at this point. Yes. Pardon, say that. I mean, remember that I'm not worrying about any sort of endoscopic anything here. I'm just strictly working on sort of this symmetric squared lifting. So I'm not worrying about endoscopy at all. Just no. Just a map between L groups. This is a beyond endoscopy thing. Yep. Yes. Yep. Oh, yes, no, absolutely. So, yes, because I'm working in these fairly restricted cases, we can sort of use more simplified data to deal with our characters. If we wanted to do cases beyond just GL, we would need sort of a more complicated setup. But for supercuspidal characters of GLL, we don't need all the extra baggage of used datum. We can basically just look at pairs of tori and characters. Yeah. Yes, yeah, because remember we're dealing with stable characters, and stable characters of SLL are just characters of GLL restricted down. One could, but in this problem we wouldn't want to because we care about the stable characters here. So we don't want to separate them out here. Yeah. No, because we're dealing with a separate case here, which is just the stable transfer. So the endoscopic case deals with the other side, but we're just considering the stable case. Yeah. Okay. Sorry for going over. Thanks.